the other example will be on a truss system. Okay, and so as you already know that flexibility method is basically used for indeterminate systems. For determinate systems, you don't need the flexibility method because the very first part of the flexibility method itself will solve a determinate system. Okay, so this is the frame that we will solve today, but I will solve it by hand using an like slides for solving an example kind of gets boring, right? So I'll try to do it as I'm talking about it. So let's say this is the frame is this one. Okay, we'll call it example 2. That's one example we did already while we were trying to explain the method. Okay. Now the boundary condition here is this one, which you can call a slider. Okay. All these examples are already there in your lecture notes. Fine. Both lengths are given as L each. So hopefully today's class will be the last class for flexibility method so that we can move to the stiffness method. That is the main content of this course. Okay. So first step would be, what would be the first step? You already know, that's why you're not telling me. Everybody knows it so well. Yeah. Somebody? Start with?
When finding starting indeterminacy.
Static indeterminacy, right?
Yes, sir.
Yes. So for the static indeterminacy, since this is a frame system, this joint between the vertical member and horizontal member, that is given as a fixed joint. Couple of other information, the flexural rigidity, I forgot to mention that, flexural rigidity of each member is uniform, that is EI. Both members have a flexural rigidity of EI. Okay. It is not a stiffness, it is rigidity. That is a cross-section property, EI. Okay. If I had said EI by L, EI by L square, EI by L cube, then it would have been a stiffness term. But EI in itself is just a cross-section property, and that is uniform. So basically what it is meaning is that cross-section is uniform and its flexural rigidity is EI through both members. Okay, and this joint is a rigid joint. All right, so static indeterminacy, since this is a frame system, I tend to use the expression that I use for frames, that is R. Here R basically represents all the unknowns. So since this is a frame system and I don't see any special complications within the system, I can assume system to be a single system, right? So I will take just the boundary conditions here. If I had to split it into two parts, then R would change accordingly. But for now, there are R is equal to 3 here and R is equal to how much here? How many reactions am I getting here? Two reactions, right? Sorry, my mistake. Yeah. So it is restraining the movement, the rotation here, and it is restraining this movement. This movement. Okay. So these two movements are restrained. So therefore, you will have two R's here. So I've got 3 plus 2, that is R, minus 3 times N, and I've taken only single part. I did not split this into two parts. If I had to split this thing into two parts, then my R will increase by 3. So it won't make any difference. My N will increase by 1 and R will increase by 3. The equation will remain balanced or as it is, whatever it is right now. So what do I get? 5 minus 3 is equal to 2. So I have a 2 degree of indeterminacy. That is pretty obvious to see, because even if you did not have this support entirely, the system would still have been a determinate and a stable system, correct? Just from this cantilever. That means both of these degrees of freedom are redundant. Both of these constraints are redundant, the constraints that are available here. Fine. So what do we do? We need to, in step 2, we need to reduce this to a determinate system. And as you know, you can do it in several ways. But you have to be smart about it so that you don't make it unstable by mistake. Okay, so one option could have been to put a pin support here and put a roller support here. That way, I would have released the moment here, okay, and I would have released the vertical movement I have restrained. Sorry, not this one. Sorry, my mistake. I had released a moment here. So one I had released here. Here you are restraining two forces. You are restraining a moment here. Sorry, restraining a rotation here, and restraining the horizontal movement here. If I had to continue restraining the horizontal movement, but allow for the rotation, what would I do? I would simply do this. Correct? And that would have been a determinate system. Agreed?
Yes, sir.
Yeah. Alternatively, what I have decided to use is to maintain the fixity here and release both degrees of freedom here. Okay. So what have I released? So these were the 2 degrees of freedom which were restrained. This we can call m theta. This we can call r or delta. What I mean by this is that earlier the moment value was non-zero and theta was 0. But now what I am doing is I am making m as 0, moment is 0, but theta is non-zero. Okay. Same thing with r. So earlier the r was non-zero, delta was 0. It was restrained. But now what I'm doing, I'm making delta 0. Sorry, delta was 0. Now I'm making r as 0 and making delta non-zero. Okay. So that's what is called releasing that degree of freedom. Fine. If I were to do this, my unknown forces or my redundant forces that I released would have been, or the degrees of freedom that I had released would have been theta here and would have been theta here. Correct? But now what I have is theta and delta at this location. Okay. So we will not discuss this any further. You could have gone that way. There was nothing wrong with that approach, but I have decided to go this way. Fine. Okay. So now this is turned into a determinate system. Now what is the next step? Can somebody tell me what is the next step? From yesterday's previous classes lecture notes, what is the next step? Step 3.
Solving the determinate system for external and the redundant forces.
Correct. Solving the determinate system for, there are 3 loads. So one, I did not mention what load it was supporting. In the problem, I had a uniformly distributed load acting on the horizontal member. Okay. So we need to solve the system for that load. So for the external load or real load, that I'll call W. Okay. Just because I'm already calling that W there, that's why I'm calling it W. And R and M. So solving this system for W, R, and M. Okay. Wherein W is the real force and R and M are the redundant forces that I have released. So essentially it is for two types of forces, real and redundant. Okay, we'll start. We will make 3 columns. This is the frame. Determinate here. So I'll just put this boundary condition. Load W is applied. And what do I want to know when I say I want to solve here? Of course, I want to know reactions, etc. But reactions you can get easily. What I actually want to know. For that, you must know what is the next step. The next step is to calculate the deflections, right? After solving, I would require to calculate the deflections here, deflections and rotations here at this free end. And for calculation of deflections, what do I need? Bending moment diagram. So basically, I want to know the bending moment diagrams when I solve it. Fine. So bending moment diagram is not something too difficult to do here. I'll just create a gap here between the two members. Okay, so there is a vertical member here, there is a horizontal member here. Now, if it's a horizontal member only and this W load is acting, and the only support you have is at this end, okay, that at that end you are getting the entire fixity. So what would this horizontal member be behaving like? You have a horizontal member projecting out. There is a very simple system. That is what this horizontal member is behaving like. What is that system?
Cantilever.
Right? Cantilever. Exactly. So you already know the bending moment diagram for a cantilever, right? And I'm plotting it upward because it's a hogging moment. Okay. Right. So how much will be this moment? Okay, and I'll call it minus because that's my sign convention. Fine. Any surprises, confusing things here? None, right? Now, as far as vertical member is concerned, what is happening is if you draw the free body diagram of the two parts, the free body diagram of this part will suggest that there is a vertical force acting on the horizontal member here, and there is a moment acting in the counterclockwise direction to balance the moment because of the external load. Now, as Newton told us in his third law, that there will be an action and reaction, right? So this moment that I have plotted here, this moment is acting on the horizontal member. But which member is applying that moment on the horizontal member? Who is applying that moment?
External load.
No, external load is causing it. So if external load was acting, but this member was floating in the air, this moment would not have been there. Okay, the horizontal member would have just gone in a spin. Okay, so external load and Newton's first law is making sure that this moment is there. But according to Newton's third law, so if this moment is there, that is being applied by something else. That is being applied by the vertical member. Okay, that means this horizontal member is also applying another moment on the vertical member, and that is this moment that I've just drawn. Okay, that means this is the vertical member. It has a fixed boundary condition. You have a moment acting at the other end. So again, you can imagine that this is a cantilever. Plus, in addition to that, there will be vertical downward force. But vertical downward force will be purely an axial force, and it will not contribute towards the moment. So you can ignore that for bending moment diagram calculation. Okay. So it is there, but I'm not considering that for bending moment diagram calculation. So basically, you again got another cantilever. In that cantilever, you have a moment acting at the free end. Now, for that kind of a problem, a cantilever with a constant moment acting at the free end, what is the bending moment diagram? If I draw the moment on the tension side, it's a uniform moment.
Uniform.
Okay. And as you know, this moment was equal to actually the bending moment of the beam at this end. So this moment is basically equal to WL square by 2 in this direction. Okay? So that is what exactly the moment here will be. Okay? I'm showing the arrows to mark the direction. Okay? Otherwise, you keep confusing whether this is the beam or that is this side is the beam. This is the beam, and I'm marking my moments on the other side. Okay, and the value is WL square by 2. Now you can call it minus, or since I was calling this one minus, I'm calling this one also minus, but that is up to you. For horizontal members, we usually don't have a sign convention of which side is positive, but you have to be consistent. If you are calling right hand side moment, or when you are plotting, so basically my sign convention is that I plot bending moments on the tension side. So that's how I have drawn it on the tension side, WL square by 2 on the tension side. Now, if your tension side is right side, okay, like in this case it is left side, tension side is left side, then in subsequent steps, if the bending moment is drawn on the right side, then that has to have different sign. That's what you have to make sure. Okay, so we have solved it for W. Now the second step is solving it for R. Fixed here, and we are applying an R force here. Fine. So we will again break this into two parts. I'm just going step by step so that all your doubts, if any, about the free body diagram system, that is also resolved, so that you never have that issue in future. So an R force will be acting here on the horizontal member, and if this member is not held back by something else, then this member will fly away. Okay, but we don't want it to fly away, or it is not really flying away. So that means it is being held back by another force R here. Okay, I'm erasing it so that I can draw the forces on the other member. That means this member is being pulled in this direction by force R. Why? Again, Newton's third law. So this one was pulled in this direction by force R. By whom? By member. Let me give them some names. Otherwise, A, B, C. Okay. So you got A, B, C. So member BC is being pulled back by a force R by member AB. And then member AB is being pulled forward by member BC at location B by force R. Okay. Now again, to balance the force, at A, it is being pulled back by the boundary condition. Fine. But this is leading to a large moment demand, unbalanced moment. This force has to be R2 for equilibrium. Now, equilibrium is not satisfied yet. That means these two forces are making a couple, which is going to turn the vertical member AB, in the clockwise direction. So I must have, for the system to be in equilibrium, I must have an external moment in the counterclockwise direction. So that is the moment acting on the vertical member AB. Okay. So from here, I can draw the bending moment diagram. So was there any bending moment acting on the horizontal member? Member B? No. Right? There was no moment acting. It was very easily in equilibrium. Was there any moment acting on the vertical member? Yes. The bending moment, if I can take a look here, if I move in this direction by distance x, then R multiplied by x will be the moment required to keep that in equilibrium, right? So basically what I get is, the direction is counterclockwise. That means this side is in tension, this side is in tension, same as before. Okay, so I'll draw it this direction. Everybody understood why I'm drawing it in this direction, right? And what is the value here? If I'm at a distance x, the value here is Rx. Since I'm calling the moments in this direction, left direction, on vertical members as negative, I'll call it minus Rx. Fine, everybody on board? the value here will be minus R times L. Solve. So we have solved it for W and R. Any questions so far? Similarly, we can solve it for M. Again, free body diagram. I have a moment acting M here, external moment acting M on the on member BC. Okay, member BC has a moment, external moment acting at point C. Okay. The only way you can balance it by applying an equal and opposite moment of value M at point B. Okay. Now you cannot get that reaction from just anywhere. You have to have a member connected to that end, which will provide you that support or a boundary condition. We do have a member AB that is connected to member BC at B. That means member AB is supplying that moment, which also means from Newton's third law that member BC must be applying equal and opposite moment on member AB. Fine. And now this member is not in equilibrium. So of course, the boundary condition has to balance that in opposite direction. Okay. So this is the free body diagram. You don't need any other forces or moments to make it in equilibrium. The values are all M. Okay. Now here, if you look closely, which side is tension side in each member? For the horizontal member, which side is tension side?
Bottom side.
So that is opposite of before, opposite of what we were having when W was applied. Okay. So we will draw it on the bottom side. What will be the bending moment diagram? It will be uniform M.
Straight line.
Yes, uniform. Is Kelvin attending the classes now? Kelvin, are you there? Okay. So since I was calling the upward drawn moments as negative, downward drawn moments I'll call positive. Okay. Similarly, since I was calling the leftward moments as negative, bending moments as negative, this one will be rightward because you have tension on this side, right? So I'll call these as positive. Okay. What is the next step? What would be the next step?
Deflection calculation.
Which deflections do we calculate? Which deflections? Theta and delta, right? Calculate deflections. Theta and delta for each. Okay. Again, we will go step by step. So first we will calculate deltas and then we will calculate thetas. Delta due to W. Or I'll put W at the bottom. Okay, calculate delta due to W. Now we will use virtual work method. What is the virtual work method? What do we do? First, we apply the virtual load. The way I do it, you can apply it. You can inverse the order, reverse the order. I tend to apply the virtual load first, right? So if I want to calculate if I want to calculate delta, I have to apply the virtual load in what direction? If I want to calculate delta, what is delta? Delta is this movement, right? that we had released. Right? So that moment. So if I want to find the value of delta, the virtual load has to be R is equal to 1. If I want to calculate theta, the virtual load has to be M is equal to 1. Okay. So external work. What was the definition of external work that we were using? External work is the work done by the virtual load while the real loads are being applied. So the virtual load is acting in the direction of delta, right? That is R is equal to 1. Virtual load is that one, R is equal to 1. We apply unit virtual load and it stays there. Then we apply W. And when W is being applied, that R is equal to 1 is moving, is riding along. And that is doing some work. And that is that work. So how much work it will do? R, I'll call it 1, basically, multiplied by delta due to W. So how much ever delta takes place because of W, that multiplied by 1. That is my virtual work. And the virtual work method employs this theory of energy conservation or energy equivalence. So your W external will be equal to strain energy of the system, and the strain energy will be U, which will be an integration of M real, M virtual divided by anybody? EI dx, right? Am I right?
Yes, sir.
Yes. So that is M virtual M real divided by EI dx. Okay. So W external was equal to delta W. So I'll just call it delta due to W. And that is equal to, now what is M real here? That is this bending moment diagram that you can see here, right? Right here, this bending moment diagram. And M virtual will be basically the bending moment diagram because of R is equal to 1. That is given here. Okay. So we just need to multiply the two. Now, as we can see that the M virtual for the horizontal member is 0. So we don't have to do any calculation there. The integration of 0 will give me 0 only. Right. So that value will be 0. Will be equal to integral. I'll only do this calculation for the vertical member. For the vertical member, M real is equal to, since both of them are minus, anyway I'll write it. W L square by 2, that is M real, and then M virtual is minus Rx, and R is equal to 1 here, so minus X. Okay, dx, and I'll take by EI. And there is no horizontal member does not have any strain energy. That will be equal to, minus and minus will cancel out, WL square by 2 EI, and X will be X square by 2, so L square by 2. That is W L to the power 4 divided by 4 EI. And that is my delta value equal to, delta value because of W. You got it? Fine. Also, let's calculate theta because of W. Okay. So now, what I'm trying to do is I'm trying to calculate how much rotation it will take place here because of W. And for that, wherever I want to calculate the rotation, I have to apply a unit moment there, virtual moment. And that is what this solution is already available to me. I can simply use that. Okay. So what am I going to do? I'm going to apply this moment here, which is equal to 1, and then solve the same thing. So again, virtual work, external virtual work will be equal to this unit moment multiplied by theta caused by W. So W external will be equal to unit moment multiplied by theta caused by W. Fine. And that is actually equal to U, that is your strain energy. Now this time both members have non-zero values. So this moment is non-zero, this moment is non-zero, this moment is non-zero, this moment is non-zero. Okay. So we have to solve it for both systems, both members. So 0 to L. I'll first solve it for the vertical member. For the vertical member, it is WL square by 2 minus WL square by 2, correct? Multiplied by, the other one has how much moment? So this one was minus WL square by 2 here. This is minus WL square by 2. But this one has plus M. Okay. And now M is equal to, M is virtual load, right? So M is equal to 1. So that is plus 1. Multiplied by 1 dx EI. Okay. Plus, for the other member, for the other member 0 to L. Now for the other member, the bending moment diagram was not constant. It was not WL square by 2. It is minus WX square by 2, isn't it? For the horizontal member, multiplied by, again, bending moment from the uniform external moment applied is 1 dx. You are following it, right?
Yes, sir.
Okay. So from here we can get theta W is equal to, following these two systems. So this is going to give me Wx square dx. So Wx cube by 3. Okay. So Wx cube by 6. So our first one is first going to give me minus W L square x. So L cube by 2 EI. Again, minus W this will be x cube by 3. So x cube, so that will be L cube by 6. That 3 multiplied by this 2, 6 EI. Okay. This is 1 by 2 plus 1 by 6. How much is it? This is 1 by 2 plus 1 by 6, right? 2 by 3. Okay. Is that all right? So I got,
Yes, sir.
yeah. So I got theta. I got delta because of external work, external force. Similarly, I need to calculate theta and delta because of this R and M as well. Okay. So again, calculate delta, sorry, R. Okay. There is a power cut at my place. I hope you can still hear me, right?
Yes, sir.
So this time what is happening is that I want to calculate how much is the horizontal delta at this point because of the force R. Okay. Now R and delta are already in the same direction. Okay. So actually, ideally you should have divided by 2, but since it is on the both sides, I'll not do it explicitly. But ideally you should divide it by 2. But anyway, so delta because of R multiplied by 1. Okay, 1 is the virtual load. So first I'm applying R. So first I'm applying virtual load 1, and then I'm applying R in the same direction. And when I'm applying R, then the system is deflecting by delta. Okay? Delta because of R. So delta because of R multiplied by the virtual load 1 will be equal to U. That is equal to, again, the horizontal member has 0 moment, so I don't have to worry about that. The vertical member only has a moment, which is minus Rx. That is because of R. And the moment because of virtual load is minus X. Correct? Because virtual load is unit. Dx divided by EI from 0 to L. So delta because of R will be equal to minus and minus will cancel out. You got R outside, X squared, so X cube by 3. So X cube by 3, and since it is 0 to L, I can call it L cube by 3 EI. Okay, R L cube by 3 EI. Fine. Similarly, I can calculate theta because of R. Now for theta because of R, what am I saying? I want to know how much rotation, this beam has at this free end because of R. So for the rotation, in order to know the value of rotation, I have to apply a virtual moment. Okay, M is equal to 1. Or in other words, I have to take this bending moment diagram and this bending moment diagram, the second and the third one, and multiply. So again, repeating the steps, external was equal to theta of R multiplied by one moment, unit moment. Okay, that will be equal to U. That will be equal to, again, there are two members, right? Vertical and horizontal. The vertical member has a non-zero moment, but the horizontal member has 0 moment. So there won't be any integration coming out of there. I'll do only vertical member. Okay, vertical member had a bending moment diagram of, or bending moment of minus Rx, and the vertical member here had a bending moment of plus M, so plus 1, because M is equal to 1 here. That is the virtual moment, dx divided by EI, and that gives me theta because of R is equal to, R will come out minus X, so that X will give me X square by 2, L square by 2, so minus R L square by 2 EI. Is that correct? So maybe I'll just put these in two boxes. So what is this delta R and theta R values that I've just calculated? You remember in the flexibility method, what are these terms called? Delta R and theta R. Or if I just substitute R is equal to 1, then what will be these? What will these be called? If R was 1.
Flexibility.
Flexibility, yeah. So these are flexibility metrics terms. Okay, these are the two different terms of flexibility metrics. Fine. So for a unit R, how much is the deflection? For a unit R, how much is the rotation? This is flexibility. There are total 4 unique terms in the, not unique terms, 3 unique terms, 4 terms in the flexibility matrix. Calculate, next step would be calculate delta because of M. Fine. So again, W external. Now I'm talking about delta because of M. So if I apply a moment here, it is going to have a deflection. Okay. And I want to know how much deflection does it have in this direction, in the rightward direction. So for that, I have to apply a unit R. Okay. So delta because of M multiplied by unit R, that is external work. That is also equal to strain energy, and which is equal to, now I need to take the bending moment diagram. So this one is the virtual, R is virtual now, and M is real now. M is real now. So I have to substitute R is equal to 1 here and multiply the two bending moment diagrams. This one has 0, so I just need to take care of the vertical one, 0 to L. On R will be equal to 1, so minus X. So first let me put this one, plus M minus x dx divided by EI. So from here, delta M turns out to be M minus x will have an x square by 2, L square by 2, minus M L square by 2 EI. All right. Moving forward, calculate theta because of M. Now if you notice, I'm saying how much is the rotation because of this M? How much is the rotation at this point because of this M? So I'm looking at the same load and the deflection in the same direction. So ideally I should divide by 2, but again I'm just going to skip that part. That detail, basically I'll just not divide by 2, but ideally I should. So, but if I'm going with the virtual load method, then I don't have to. So W external will be equal to theta because of M multiplied by 1. So 1 is the virtual moment. So what I'm saying is, first I apply the virtual moment 1 in the same direction as M. Okay. Then I apply actual M. And when actual M is being applied, then during that time, this 1 was doing some work. And that's what I'm reporting here. Okay. Will be equal to U. That will be equal to. Now, both parts have non-zero terms, vertical and horizontal. But one is M, and from the other one, you are getting 1 dx by EI. Okay. Again, M, 1 dx by EI. Okay. So your theta M will be equal to M L by EI twice, 2 times, not 2 EI, sorry. M L by EI. Fine. So this is the deflection and rotation because of M, and these are deflections and rotations because of R. So these 4, this one, this one, this one, and this one, these 4 are my flexibility metrics. I just need to take R and M out to call them flexibility metrics terms. And these are the right hand side of that equation. You remember what was that equation? This was my flexibility matrix multiplied by R and M, and was equal to delta and theta. Correct? So that as because of W. Okay, that is that term. Now we need to enforce. What is the next step? Step 4 is done. The next step would be step 5.
Solve for R.
Mostly compatibility conditions.
Yes.
Compatibility.
Compatibility. Fine. So basically, I have to make sure that total delta because of W plus delta because of R plus delta because of M is equal to 0, and so is the theta. Okay. So we see WL to the power 4 by 4 EI, RL cubed by 3 EI, ml square by 2 EI. So I'll just write the equations and solve the equations. Basically, solving part, you can do it on your own. The first equation will give me R L cube by 3 EI minus ml square by 2 EI is equal to minus WL to the power 4 by 4 EI. Okay, that is this equation. And this equation is bringing me R L square by 2 EI plus 2 M L by EI. Sorry, minus is equal to minus 2 by 3 W L cube by EI. Okay. So again, it can be written in the matrix form as I explained before.
Sir, minus.
Did I miss something? RL square minus 2.
Minus R square.
I believe I am correct here. So which one? Second equation you have a problem with?
Yes, sir.
Is it it should not be, it should be minus RL square, you think?
Yeah.
Theta, right? So yeah, so let's put it negative here. Let's take a minus of this one. So RL square, then theta M. I'm doing a minus of this one, which is okay. And this is minus, but I'm taking it to the other side. It's okay. I think it is correct. I just multiplied with minus 1 the whole thing,
Okay.
just to keep our terms as positive. Just check again, just in case there is a mistake, but I suppose it is correct. Okay, and the terms you will have here is L cube by 1 by EI. Of course, you will have outside that EI can actually cancel the other EI out. Okay. L cube by 3 is L square by 2 minus L square by 2, that is obvious, and 2L. Okay, now as you can see, this is a symmetric matrix because this term is equal to this term. So this is a symmetric matrix. That is what it's supposed to be. Fine. I have removed the EI terms. These were just on both sides of the equation. And you can solve using this one. R turns out to be minus 0.4 times WL and S. And M turns out to be 0.23 times WL square. Okay. What does the sign mean here? I had assumed that my frame when I was studying the solution, I had assumed an R value in this direction and M value in this direction. So M is correct in the sign, but R is wrong. That means the actual R of the actual forces that are external forces that are acting on this one in this direction are 0.4 WL in this direction and an external moment of 0.23 WL square in this direction. Okay, and then of course you have W acting here. So this is another determinate system in a way, if you can call it. This is a determinate system. The redundant forces that you had removed are actually now available to you as known values, known external forces, and now the rest of it is a determinate system. You can solve this system again and calculate the entire bending moment diagram. I have not repeated that exercise, but I would strongly encourage you to practice that once. All you have to do is, you know the bending moment diagram because of a given R here. You know the bending moment diagram for a given M here, right? And you know the bending moment diagram because of W. All you have to do is multiply by that bending moment diagram, the second one, with this minus 0.4 WL value, and similarly the third one you multiply with 0.23 WL square. Okay, and Then you already know the bending moment diagram for W, this W value. So you add the 3 and you will get the final total bending moment diagram. Likewise, the reactions. Okay. Any questions? Okay. Fine. Yeah. Any questions? Okay. In that case, I'll move to the next example. I want to complete both examples today itself. So this one was example 2. So I'll take example 3 today. Now, okay, this will be a truss. Now, making a truss into an indeterminate system, either you play with the boundary conditions that you can do very easily. So if I have a truss like this is a, what kind of truss is this? Is it determinate truss or an indeterminate truss?
Determinate.
Truss, right? How do I make it indeterminate? There are two ways, or several ways rather. I mean, but there are two fundamental ways. One is I can increase the number of boundary conditions. Okay, so I can add this boundary condition, which will restrain the movement in this direction, which will essentially make it an indeterminate truss. Fine. Alternatively, I may have an indeterminate truss that has another member added to it. It's not like a straight line. Try drawing it again. Okay, so another member added to it. Now the trick here is, or what you need to understand here is that there is no connection between this member and this member in this area. Okay, they are not connected. They are separate members. Okay, and in a way you can think of them as if they are sliding over each other. Okay, then this will be an indeterminate system. Okay, so let's say this is the problem that we want to solve. An external load of 2 kilonewton is applied. Member numbers are given A, B, C, D. Okay. The dimensions are 4 meters here and 3 meters here. Okay. So the diagonal member will automatically be 5 meters long. Okay. The step 1 will be, the first step will be indeterminacy, static. So we already know, just now we did that. We had a determinate system and we only added one member to make it indeterminate, right? So the indeterminacy is 1. But just to satisfy our curiosity again, I'll use that expression B plus R minus 2J. For trusses, I tend to use this one. And you don't have to use this particular method. You can use whatever method you are familiar with or comfortable with. B is number of bars, that is 6 bars are there. Plus number of reactions, I've got 3 reactions here. 2 reactions here, 1 here. Minus 2 times number of joints. I've got 4 joints. So 9 minus 8, that is 1. So I've got 1 indeterminacy. Fine. So now the step 2 would be to reduce this system into a determinate system. How do we do that? So as I had just shown you that we had added one member in the structural system. So we can simply cut that member, right? That would be very easy to do. Let one diagonal member be there. Okay. Let let me cut the other diagonal member. Somewhere here in the middle. You can cut it anywhere, but I'm just thinking that somewhere in the middle I've cut it. And even though I have not changed the orientation, I'm just plotting it in such a way, drawing it in such a way so that it looks like it is separated. Or rather, let me, sorry. It is separated. I'm just drawing it slightly off so that I have more space to mark things here. But actually they are aligned. And now between the two, I've got a gap here. Why is that gap there? This gap. And that is because I'm applying the external load of 2 kilonewton still. Just to keep it easier. I've not changed the alignment just to avoid the confusion. There is a gap of, and I'm calling that gap delta AC. This member is AC, right? A, C, and T. This is delta AC because of the external load, 2 kilonewton. Fine. So in member AC, I'm going to get a separation because I have cut the member and the member does not have a continuity. That means it cannot resist any load. This is a determinate system. But now what will happen is that this member that I have cut, that is basically one redundancy I have removed. But that actually was there. So when I did this like removal of this redundancy, I artificially changed the force in member AC to 0. Okay. So in this case, when I am applying this 2 kilonewton external load, this member AC is not carrying any load. It is simply it is basically moving away from each other as if it is not a continuous member, right? But in reality, it is a continuous member. So what I have done artificially here is that delta AC, which was actually 0, I have made it non-zero, and the force AC, which was actually non-zero, I have made it 0. So this will be the second part of that. If we were to enforce the compatibility condition, this is what I have to do. This time I will misalign them slightly so that I can draw. I have space to draw. Okay. And here what I am doing is I'll apply an FAC force. That is my unknown force. That was my redundant force that I had released. Okay. And boundary conditions are still the same. So now here you have to be very careful how FAC is being applied. If you notice, I am not applying a single FAC. The force FAC is actually a force couple, right? It is acting on both sides of that member, and that is very, very important here. Okay. What I have done here is I have cut a member. If the redundancy was of this kind, which I could handle with a boundary condition. So, for example, if the truss problem was this one, you are following me, right? So far, if the truss problem was of this kind, as I had mentioned before, the redundancy that I had to remove was simply this boundary condition, and I would have applied an external force. Just like I did in the previous example, I removed some boundary condition and I applied the corresponding unknown force or redundant force. Correct? But in this case, the redundancy is not coming from a boundary condition. So that force cannot be a net net force. It has to be a force which is balancing itself because I am cutting a member, right? So that internal force is being released. So that internal force I have to apply. That internal force is the unknown force. Okay. Therefore, I have to apply FAC here and FAC here to properly capture that effect. If I had applied, for example, this was the truss, and I apply FAC only here, that would be wrong. and not applying FAC here. That would be wrong. This is wrong. This is correct. You follow it, right? Because it's an internal force that I am releasing. I was releasing an internal force, so I have to apply that internal force. And internal force by definition is balanced, self-balanced. So I have to apply both. Boundary conditions are the same. Keep the numbers A, B, C, D. Okay. Now, since there is only one redundancy, there will be only one unknown force. Step 3 would be like before, solve the determinate system for W, which is external force, right? Or 2 kilonewton, let me write it. You can give it some name also, I'm just keeping it 2 kilonewton. And FAC. Okay, because there is only one redundant force, FAC. If in the earlier problem we had 2 redundant forces, so there were 3. There were 3 times we had to solve it. This time we have to solve it only for 2 forces. One is 2 kilonewton. So, okay. Point again, let me see if I can copy paste this. Beautiful. Okay. All right. So this external force of 2 kilonewton is acting here. This 2 kilonewton force is acting here, and this member will be the member that has been cut. Member AC will be carrying 0 force, right? This is 0, obviously. This is obviously AC is carrying 0. Now, if you see at joint C, you got. Let me draw the free body diagram of joint C. You got 2 kilonewton force acting here. Okay. This is 0. This is some resistance. What will be the force in the vertical member CD? As
0.
while we know AC is 0. Yeah, so this will also be 0. Exactly. So force in member CD will also be 0 because there is no other force which can balance that. So therefore this will be 0. And what will be the force in member BC?
2, sir.
Tension. 2 tension.
Okay.
Tension of 2. Okay. Now draw the free body diagram of joint B. You got a tension force of 2 acting here. Okay. It has to be balanced by this force here. It has to be balanced by this force here. Okay. So how much will these forces be? This one, the diagonal one, has to be 2 times 5 multiplied by 4. Where did I get 5 multiplied by 4? That is the ratio of the dimensions. So 5 is the length of the diagonal member and 4 is the length of the horizontal member. This length is 4 and this length is 3. Right? So I'm just multiplying with that 5 multiplied by 4. So which will basically give me 2.5. Correct? So that is 2.5 in this direction, and it will basically mean 1.5 in this direction. So 1.5 in tension in member AB. Does that sound okay? Look okay? And minus 2.5 in compression. Minus. I'm using minus sign for compression and plus sign for tension. Okay. Have I solved for all members already? Member AD is remaining. So member AD I cannot solve from A because A is a pin support. So it will absorb all the forces that are coming to this member. It will not give me any additional information. Member joint D I have to solve. So joint D has a compressive force coming from BD. That is, this is push force of 2.5. Okay. Then you got a vertical support. That means it can apply a vertical load here, whatever you require. So vertical balance, you don't have to worry about. That will be taken care of by resistance from the support. Only thing that you have to worry about is horizontal member force AD, which will be equal to 2.0, right? You got tension of 2. Okay, so I have solved the system for the external force 2 kilonewton. The second part is to solve the system for an FAC force. That is my redundant force. Okay, so let me solve it for FAC is equal to 1. Whenever I need to use FAC, I will use that. So if this force is 1 here, again, joint A, B, C, D. So let me start from joint C. Joint C, at joint C, I have force 1 acting here. Force 1 acting here. Its horizontal component will be, since the ratio is 5:4, will be 0.8. Okay, and it's in opposite direction, sorry. In order to balance, or in order to keep joint C in equilibrium, I have to have a 0.8 force acting here. And how much force should be acting in this direction? Anybody? How much force should be acting here? 0.6, right? So if I have 0.6 and 0.8 acting, their net will be 1 in this direction, which will cancel out 1. Correct? It's just like 4 and 3. If 4 is acting here, 4 is acting here, 3 is acting here, the net will be 5. Is that correct? Or am I making a mistake here?
Yes, sir, correct.
64 plus 36 is what? 100, right?
Yes, sir.
Yeah. Okay, so basically it tells me that this force will be minus 0.6. This force will be minus 0.8, or you can call it 4 by 5. It's your preference. Okay, moving forward, which joint can I come to? I can go to any joint that has 2 unknowns, right? So B has 2 unknowns now. Because I'm using method of joints, if you have not noticed already. So I've got 0.8 force acting here that cannot be balanced alone by the vertical member AB, but it has to be balanced by the diagonal member. So diagonal member again will have force 1, and in that way you can get 0.6 in this direction. Correct? So you get positive 1 tension in the diagonal member, that is BD force, and in member BA you get compression of 0.6. Okay. Coming back to joint, again joint A will not give you much information. Joint D, because right now we are not interested in calculating the reactions, we are mainly interested in calculating the member forces, internal forces. Joint D, we have a compression here, that means it is being pushed by 0.6 here. That I don't really really doesn't matter, because it's going directly to the support. The support will take care of it. Whatever it is, I don't mind. I don't care. This member is pulling by force 1. That is, member BD is pulling by force 1. And there is a horizontal force also that has to balance this, right? So once vertical component plus 0.6 will be taken care of by the reaction. That I don't have to worry about. But its horizontal component, which will be 0.8 in this direction, will basically give me minus 0.8 compressive force in member AD. Okay. Yeah, looks okay. So I've solved the system for internal forces too. Now the next step is calculate deflections. Where do we calculate the deflections again? Do we calculate deflections where the external load was applied? Sorry. Where do we calculate the deflection?
Where we release that.
Redundant force.
Yes, sir.
Correct. Deflections due to 2 kilonewton and FAC at delta AC. That is important. We want to calculate delta AC because of 2 kilonewton and delta AC because of FAC. Okay. So now, as you may remember, I want to know the deflection at this point, at this gap, correct? Because of this 2 kilonewton force and because of this FAC is equal to FAC, whatever. Okay. So starting with external work, W external. I'm trying to calculate deflection delta AC because of 2 kilonewton external load. That will be what it basically means. First, I apply a unit load FAC, and it is maintained while 2 kilonewton is being applied, and then the joint moves slightly, right? Or this gap is created during the application of 2 kilonewton. And during that process, this one will be doing some work. That work is what I'm talking about. So one is that FAC force, virtual force, multiplied by delta AC. Okay. And this delta AC because of 2 kilonewton. So I should not forget to mention that. Or I can write it below also. Since we are talking about only one delta, we will not write delta AC, we will simply write delta due to 2 kilonewton. I'm just trying to reduce the amount of writing. Okay, that is external work is equal to internal work. Internal work will be equal to, for a truss, you remember?
Summation of real.
Yeah. Summation of F virtual, F real, L by AE. Correct? So one F real is coming from here and F virtuals are going to come from here. Summation of F virtual, F real, or F real, F virtual. You can reverse the order. Into L by AE, divided by AE. Okay. So essentially what I'm saying is delta due to 2 kilonewton load is equal to F real. So let's start with one member at a time. 1.5. I'm starting with this plus 1.5. Member AB. 1.5 multiplied by minus 0.6. What is the length? 3. Okay. And 1 by AE. Since AE is assumed to be constant throughout, or it is given in this problem that AE is constant, uniform. I'll take AE out, but the lengths are not uniform. Each member has different length. So I have to multiply with the length individually. Plus, for the other member, DC, it is plus 2 and minus 0.8 multiplied by 4. Plus, the diagonal member has 0 force here. AC has 0 force here, so I won't have to worry. The other diagonal has minus 2.5 plus 1. Okay, so this one has 1 here. This one was minus 2.5, so multiplied by 1. I am not writing that. Multiplied by 5. Okay. Plus, member CD has 0 force, so no contribution. So member AC and CD won't contribute. The other horizontal member is AD, which is plus 2 here and minus 0.8 here, which is same as this one. So I'll simply write multiplied by 2 here. Okay. If I solve it, what do I get? I get 3 multiplied by 1.5 multiplied by 6, no, 0.6 multiplied by 0.6. That is minus. See, all terms are minus, right? All terms are negative. So I'll put negative at the end. 16 multiplied by 0.8 plus 5 multiplied by 2.5. Yeah, that is 28. So it turns out to be minus 28 divided by AE. Okay, that is my delta because of 2 kilonewton load. Kilonewton. Okay, now we will calculate delta because of AC or FAC. Again, W external. Now what we are doing is we are applying this one unit force at FAC at this location. We are applying a unit force and we are calculating how much deflection it is going to cause. Now here, if earlier problem, if you notice, we got a minus sign. What does the minus sign mean? The minus sign basically means is that when we apply 2 kilonewton load in this direction, the way it is being shown, I'm applying 2 kilonewton load laterally, the delta AC is separating, okay, which is opposite of the direction of FAC that I had assumed. I had assumed an FAC direction where it was kind of overlapping with each other, okay. When I was applying a unit force here, I was applying the unit force in such a way so that it is overlapping. So actual delta AC is opposite of that. That is, it is separation. Okay. So this minus basically represents that it is opposite of the FAC sign that I had assumed here. Now W external here, when I am calculating the delta AC because of FAC, it will be 1. Because basically what I'm saying is I'm applying unit force first and then I'm applying FAC at the same location. So 1 is the unit force first multiplied by delta because of FAC. I don't know how much FAC is there. That's what I want to calculate. Okay. And that is equal to U, that is equal to U, that is equal to again sigma of F real, F virtual, AEL. Now F real and F virtual are basically the same, except that in one case you have FAC, the other case you don't have FAC. So delta due to FAC turns out to be, for the moment I'm assuming FAC as unit, or I'm taking FAC out so that I can just simply take square of each term. Okay. So it's 0.6, right? So I'll do 0.36. 0.6 is square. That is 0.6. 0.6 multiplied by 0.6. F virtual, F real. Two forces are same basically, right? So I'll take it as 0.36 multiplied by the length is 3. Okay. And AE also I can take out. Plus, and there won't be any negatives because it is all squared. 0.64. That is for horizontal members. By the way, wait a minute. I got member AB, that is 0.36 multiplied by 3, plus also another vertical member also has the same force. I can multiply by 2 for the two vertical members. For the horizontal member, 0.64 multiplied by 4 multiplied by 2. For the diagonal member, both of them have force of 1. 1 squared is 1 multiplied by member length 5, and there are 2 members. Okay. Fine. Anybody has any problem with this? Any confusion with this? Please do ask if you have any problem. Delta due to FAC will be equal to FAC divided by AE multiplied by, what is the summation of this? 0.36 multiplied by 3 multiplied by 2 plus 0.64 multiplied by 8 plus plus
17.28, sir.
correct 17.28. Okay. What is the next step? Final step? Delta because of 2 kilonewton plus delta because of FAC, whatever it is, will be equal to 0. What does that mean? That basically you can solve you got only one equation. Why did you get only one equation this time? Because there was only one static indeterminacy or only one redundancy, only one compatibility equation. FAC, basically the two equations you equate, two values you equate, FAC will be equal to 28 divided by 17.28. Correct. That will turn out to be 1.62. Okay, that is the final answer. So you got the redundant force value, and then you can again go back and do the superimposition. So you got the member forces for 2 kilonewton, you got the member forces for unit FAC. Instead of unit, you put the value of 1.62 that you got from this calculation and superimpose the two values. You will get member force in every member. Okay, any questions? Doubts, questions, anything? All right, wonderful then. Good. So we have just in time we have completed the chapter on flexibility method. I think I have covered in enough detail. Of course, there are again various derivatives of the flexibility method, the three moment theorem and so on, but that's not really relevant here because I want to move forward into the stiffness method quickly. And the background of flexibility method was important or required to cover or to derive the stiffness method. That's why I spent 2-3 lectures on flexibility method. So in the next class, we will start with the stiffness method, and we will again try to focus more on the matrix way of solving of stiffness method so that we can use it with computers. Okay. Have you guys been able to figure out how to use MATLAB? Is there a MATLAB license available through the institute or anything? Any information on that? You will need MATLAB, so you have to find out how to install MATLAB from the institute. I think we have some licenses.
Yes, sir.
Yeah. So who has tried it so far? Krishna?
So I tried it. Almost.
Okay. Sorry, can you repeat? I couldn't hear you.
I'm almost through. I have downloaded institute license only, so I have to just install it.
Yeah, so please try it. Please make sure that you are able to do it, and then share with us, share with the other in the group how to do it.
Sure.
Okay.
Sure.
Thank you.
Thank you.
All right, guys. Thank you. Any questions you can ask me. You can also send me an email if you have any doubts. Whenever somebody sends me an email, I tend to reply within a day or two. If you are not satisfied, you can always ask in the class. Yeah, Leo.
So that last part, sir, the step 4 last part, FAC by AE into 17.28, that equation, no?
This one, 28 by 17.28. FAC is equal to 28 divided by 17.28 is not clear.
Hello?
Hello, can you hear me? Leo, can you hear me? Which part is not clear? There are three parts here. Delta due to 2 kilonewton is minus 28 by AE. Delta because of FAC is equal to 17.28. FAC is equal to 17.28 FAC by AE. And FAC is equal to 28 divided by 17.28. Which part is not clear? 1, 2, or 3?
So the how the FAC comes already we square taken no for FR and FE same no.
Okay, no. So see, the thing is, so you are saying delta FAC may in this equation. How am I having term of FAC still? Well, I already
Yes.
did that. Okay. See, the thing is that if you see the term for internal energy, that is summation of FR and F virtual. Okay. Here, when so basically I had kind of taken a small shortcut. Instead of 1, ideally I should have written FAC. And then all these terms, instead of being 0.8 or 0.6, they would have been 0.8 FAC or minus 0.6 FAC and so on. Okay.
Oh, okay.
And then when I do F virtual, I use FAC is equal to 1. When I do F real, I use FAC. So basically one of the two terms, so in this 0.36, actually what will happen is one term will be 0.6, the other one will be 0.6 FAC.
Okay,
Okay.
sir.
Okay. I hope I didn't confuse it. I kind of skipped a small
Good.
step. Okay.
Good.
All right. Any other questions? Okay, fine. So we will then meet in the next class. Next class is not a holiday, right? Diwali is on Friday or Saturday. Yeah. So we will meet in the next class. Thank you, guys.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.
Thank you, sir.